Hi geometry students, welcome to your video on the Pythagorean Theorem. I'm a big cat person, so Pythagorean cat right here will find hypotenuse. I don't really know what that means, but it's a cat and it's cute, so it's a fun distraction for just a minute. So, what is the Pythagorean Theorem? Well, the Pythagorean Theorem states that if a triangle is a right triangle, then the sum of the squares of the lengths of the legs on the triangle is equal to the square of the length of the hypotenuse. So let's start by making sure we know what we're talking about, legs and hypotenuse. So on this triangle you see here, that is a right triangle, excuse me, this right triangle down here, you have sides A and B. A and B are the legs of the triangle. Those are the legs. So they're the shorter sides. They are adjacent to the right angle. And then you have C, which is your hypotenuse. So C, that's the hypotenuse of the triangle. And it is always opposite the right angle. If you take the lengths of the legs and the length of the hypotenuse, this equation will always be true when it's a right triangle. The length of A squared plus the length of B squared is equal to the length of C squared. And you can use this to figure out the lengths of missing sides on right triangles. So sometimes the three numbers that fit the Pythagorean theorem will be integers, will be whole numbers. A Pythagorean triple is a set of three non-zero whole numbers that fit the Pythagorean theorem equation. Some common Pythagorean triples that we use in mathematics that come up all the time start here with 3, 4, 5. Let's clarify what we mean by a Pythagorean triple real quick here. Okay, so if I take the legs, 3, and I square it, and the other leg, 4, and I square it, is that equal to 5 squared? Well, that's 9 plus 16, which is indeed equal to 25. Another common Pythagorean triple, 8, 15, 17. 8 squared plus 15 squared is 17 squared. Another common Pythagorean triple, 5, 12, 13. Another set of numbers is a Pythagorean triple, 7, 24, 25. And I'll give you one more Pythagorean triple, 11, 60, and 61. So these are Pythagorean triples. They fit the Pythagorean theorem as whole numbers. Now, you will not often get a whole number as your answer in Pythagorean theorem problems because you're taking the square root. And remember that in order to be a whole number, when you take a square root, the result has to be a perfect square. And you can see that right here with the 25. So 9 and 16 was equal to 25, and 25 is a perfect square. Any multiple of a Pythagorean triple is also a Pythagorean triple. So with 3, 4, 5 here, we could do 6, 8, 10. That's a Pythagorean triple. And these sets of numbers will pop up. So it's not a bad idea to be aware that they exist so that sometimes your answers will be whole numbers. Now let's try a few problems. Okay, so in this set of problems, we are going to find the value of x for each figure. And even though it doesn't say so, I would like you to take your answers and round them to the nearest tenth. So round to the nearest tenth when you're doing the problems. Okay, so in our first triangle, take a look at what you're given, and you want to stop and think, well, what do I have? In this problem, I have the two legs. I have a leg of 13 and a leg of 23. So my Pythagorean theorem is a squared plus b squared equals c squared. And I know the legs of my triangle. So I know that a, we can use 13, so 13 squared. B, we can use 23, so 23 squared equals, and I don't know the hypotenuse, and they gave it the variable x. So I'm going to switch c to x for the purposes of doing the math for our problem, because we're finding x. So now I'm going to actually solve the equation. So 13 squared is 169. 23 squared is 529. And then when I add the two of them together, I get 698. And then I take the square root of each side. So the square root of x squared is x. And the square root of 698. Well, I know because I'm a math person that that's not a perfect square. It in fact is not. It's 26.4196, etc., and we're rounding to the nearest tenth. So 26.41, 26.4. So the length of x on this triangle is approximately 26.4. Let's do the next one. Okay, for this one, again, we have a right triangle, but we have a squared plus b squared equals c squared for our Pythagorean theorem. This time, however, look carefully at the triangle. We know the hypotenuse and one leg. So this one's a little bit different the way we have to solve this one. Since we don't know one of the legs, I'm going to change a to x, because x, right here, that's one of the legs of my triangle. And b is the other leg of my triangle. So I'm going to write x squared plus b, which is in this case is 5, equals, and then c squared, the hypotenuse squared, which is 13 squared. So I have x squared plus 25 equals 169. So this time I have to subtract 25 from each side of my equation. So x squared is equal to 144. Well, that number should sound familiar if you remember your times tables from back in elementary school. That is 12 times 12, or 12 squared. So when I square root, x is exactly equal to 12. So the x value for this one was 12, and the x value for our other problem was 26.4. Now notice the difference between our squiggly equal sign and our just straight up equal sign over here. This is approximate because I had to round. This one is exact because I didn't have to round. Excellent. Let's try the next two. In fact, when we get to the next page, why don't you try it yourself? Why don't you pause the video and try the next example yourself with your notes? Okay, so this time we have same idea, but they're a little bit more complicated, these figures. Okay, so if you're trying it yourself, pause it and try. And if you'd rather watch me do it, then that's fine. You go ahead and do that. So I have a right triangle this time, but stop and notice the right triangle is not the entire triangle you see on your screen. The right triangle is either this one or the one next to it. So let's focus on the right triangle I just outlined very poorly in red, kind of squiggly there in red. So what do I know about my right triangle? Well, I know that's right, the hypotenuse, that's 26. I know one leg is labeled with x, but I actually don't know this. Well, there is something I know. If this is 18, this entire base of this isosceles triangle, and this altitude drawn in the isosceles triangle is in fact an altitude because it makes a right angle here, then I know that 18, it is bisected by the altitude, meaning that each of those individual lengths has to be 9. That this one is 9 and this one is 9. So I know a leg and the hypotenuse. So let's write out the math. A squared plus b squared equals c squared. I know one of the legs. I don't know the other one, so I'm going to put x in for that first leg. The other leg is 9, and the hypotenuse is 26. So let's do the math. I have x squared plus 81 equals, and now I need 26 squared. 26 times 26, 676. And again, since I was finding a leg, notice when you're finding a leg of the triangle, you end up with sort of an extra step. So you didn't have to use that step in the one where I have to find the hypotenuse. So we're subtract the 81 from each side. I get x squared equals 595. I square root each side. And the square root of 595 is approximately 24.4. It's 24.39, so we round it to 24.4. So the length of x on that triangle, 24.4. All right, next one. This time we have a rectangle. Well, we learned some things about quadrilaterals last quarter. We learned that in a rectangle, that diagonal makes two right triangles. And we also just knew that because we know that rectangles have right angles. So if I draw that line down there, then I've got, indeed, a right triangle. So this time I'm looking for which one is it? Is it the leg or the hypotenuse? That's right, we're looking for a leg on this triangle. So let's do this one by, again, writing out our Pythagorean theorem. And all right, so I know x is one of the legs. 16 is the other leg, and 34 right here, that's the hypotenuse. So when I go through and do the math, x squared plus 16 squared, let's see, 16 times 16 is 256. 34 squared is 1,156. Subtract, and we get x squared equals 900. 900. I think that's a perfect square. Yep, it is indeed. The length of x in this problem is 30. So I'm going to put 30 for this one. And approximately, again, changing my equal sign to indicate that I rounded, 24.4. Okay, let's keep going. All right, this time they do look different again. This time they involve radicals. Now, radical expressions, that's one of those things you're going to want to ask your teacher to review if you have a hard time remembering them from Algebra 1. So in a radical expression, remember the square root of 5 is not a 5. Square root of 5 is saying what times 5, or what times itself, equals 5. Well, there is no whole number. That's why it's left a radical. But you're actually going to like these in these problems because they actually kind of turn out easier. So ask yourself what we're looking for. I notice in this one that we do have two legs, leg, and we are looking for the hypotenuse here, right here across the bottom. Don't be confused by the way the triangle is oriented. If it's on paper, you can always turn your paper. So again, a squared plus b squared equals c squared. And I know the legs. So the square root of 5, we'll put parentheses around it, squared. The square root of 8, I'm going to put parentheses around it, squared, equals c squared. Well, when you square a radical, you just get the number without the radical sign. Because the square root of 5 times the square root of 5 is saying what times itself equals 5. Now multiply that thing by itself. So we get 5. And then for this one, because again it's a radical, we get 8. We add them together and we get 13. 13 is not a perfect square, but when you square root this one, because the problem already had radicals in it, let's leave our answer a radical. So I can use square root of 13. Okay, and then the next one, we have a square. And on our square, we have it divvied up into, looks like two right triangles. So they're diagonal through the square here. And we got two right triangles. And this is the one we want to deal with here. Well, this one is a little bit different, isn't it? Well, let's look at how this is going to turn out. So let's see. We have a squared plus b squared equals c squared. And this time, both of the legs are x. So I have x squared plus x squared equals 8 square root of 2, the quantity, squared. Well, let's deal with this first. X squared and x squared. Well, that means I have two of them. So I have 2x squareds. Okay? 8 squared and root 2 squared, then I multiply them. That's how I'm going to deal with this right here. I'm going to square the 8, I'm going to square the root 2, then I'm going to multiply the result. So 8 squared is 64. 64. Square root of 2 squared is 2, so times 2, so 128. And now I have an equation that I can solve in 2 steps. I can divide off the 2, leaving x squared equals 64, square root each side, and x is exactly 8. This one came out nice and even. Okay, this one's also a bit of a preview to something you'll see in a later lesson about special right triangles. That one's actually a special right triangle. Okay, continuing on, let's look at the converse of the Pythagorean theorem. Now, if you think back to logic, we learned quite a bit about converse, inverse, contrapositive. The converse is where we switch the two sides. So remember that to be, in order the Pythagorean theorem fits right triangles. This is saying if the sum of the squares of the lengths of the two sides of a triangle is equal to the square of the length of the remaining side, then it's a right triangle. So it's taking the Pythagorean theorem and flipping it. So instead of saying it's already a right triangle, they're going to ask you, is it a right triangle? And you figure that out by actually plugging the sides into the Pythagorean theorem. So when I'm given 3 numbers, I automatically know that the largest number has to be C, and then the other 2 are actually interchangeable for A and B. And if the sides fit, then the triangle is a right triangle. But wait, there's more. If C squared is smaller than the sum of a squared and b squared, then you know that the triangle is acute. That should make sense because that means that this angle between A and B has to be smaller for c squared to be smaller than their sum of their squares. And then, of course, the opposite is also true for obtuse triangles. If c squared is greater than a squared plus b squared, then the triangle's obtuse. So your challenge is to determine if the three measures that you're given are the sides of a right triangle, an acute triangle, or an obtuse triangle. Then you got to justify your answer, and when we say justify your answer, we do indeed mean with math, with mathematics. We want to show the math to justify our answer. Okay, so you have three numbers, right? So what you're going to do, I'm going to put one big Pythagorean theorem at the top, and we're going to do the math and figure it out. Okay, so for this first one, 32, 30, and 16. Always put the largest number in for C. In fact, if it's easier for you to have an always do this kind of instruction, always put them in order from least to greatest, A, then B, then C. That way you always put the biggest one in for C, and even though the other two are interchangeable, you'll make sure you're putting the biggest one in for C instead of just going from left to right or something like that. So let's do the math. 16 squared is 256. 30 squared is 900. And when I add those together, I get 1156. And 32 squared is 1024. So c squared in this problem, c squared is less than a squared plus b squared, which makes this an acute triangle. Okay, on to the next one. Okay, now for the next one. Again, a squared plus b squared equals c squared. Okay, so this one, we have 24, 32, and 40. So again, I'm going to put the largest one in for c squared, 32 for b, and 24 for a. All right, so let's math. 24 squared is 576. 32 squared is 1024. We just totally used that one, so I'm not sure why I did it twice. When you add the two together, you get 1,600, which guess what? 40 squared is 1,600. So since they are equal, that one's a right triangle. Okay, and finally now, for the last one. Okay, last one. A squared plus b squared equals c squared. This time I have what kind of triangle? Well, guys, if two of them are equal, two sides are equal, then that's an isosceles triangle. So 11 squared plus 11 squared, which doesn't mean it can't be a right triangle, by the way, because remember, isosceles is about sides and right is about angles. So the question is, does 11 squared plus 11 squared equal 15 squared? And I'm pretty sure it doesn't already, but let's figure out, is it acute or obtuse? Well, 11 squared is 121. 2 times 121 is 242. And 15 squared is 225. So a squared plus b squared is greater than c squared on this one. Therefore, this triangle is obtuse. Okay. The last thing we have to learn how to do with the Pythagorean theorem for today is to deal with word problems. So my first direction when you're dealing with a word problem for the Pythagorean theorem is that you should draw a picture. It doesn't have to be fancy. I tend to draw my pictures with stick figures. In fact, I'm going to show you a couple of the pictures that I drew for this. Please don't laugh at my pictures. Stick figures are people too. So we're going to draw a picture, then we're going to use the formula. You want to stop and make sure that you know if you have the legs or the hypotenuse and a leg in the problem. So let's take a look at a couple of word problems. Example 1. You're locked out of your house, and the only open window is on the second floor, 20 feet up. You need to borrow a ladder from your neighbor. The ladder must be set 10 feet from the house so as to avoid damaging the landscaping. So that's like the bushes and stuff on the ground in front of your house. What length ladder do you need to reach the window? So you've learned the Pythagorean theorem at this point. I want you to pause your video. I want you to draw yourself a picture of this situation and try to figure out how to solve the problem using the Pythagorean theorem. In a moment, I'm going to bring in an image that shows you the picture and the solution. So make sure you try it yourself. That means pausing your video right now. But here it comes. All right, I'm going to make the image larger so that you can see it, but I drew the little house. It's not a stick figure, but it's a house. Okay, and I drew the window. Be quiet now, it's a window. Kind of looks like a house. I mean, it has like the roof. I mean, I can draw like a 6-year-old, but you know, not much better. So the height above the ground, the distance from the house that the ladder has to sit, and we don't know the length of the ladder, so we're finding the hypotenuse. So 10 squared and 20 squared equals c squared. 100 plus 400 equals c squared. 500 equals c squared. And that means that solution to this problem is, the solution of the problem is, the ladder must be at least 22.4 feet in length. And actually it was like 22.3 something, 3606, so you have to round it off. So 22.4 feet in length. Let's try one more problem. All right, so here's my stick figures. Here's Anna with her kite. Here's Emily standing underneath the kite. 50 meters of kite string. They are 35 meters apart. And then there's B, which we're going to use as the height above the ground for that kite. Okay, so in this case, we're finding a leg. Now, I know I usually make A the missing one, which we totally could have done, but this also worked. So we put 35 in for one leg, B for the other, 50 for the hypotenuse. So 1225 is 35 squared plus B squared. 50 squared is 2500. B squared equals 1275 when I subtract from each side. Square root 35.7, which makes the answer to my problem. The kite is about 35.7 meters off the ground. And that's all we have for learning how to use the Pythagorean theorem. Hope you enjoyed it. I'll see you guys in class.